Just let me share. Okay, so those of you who missed last class, how many of you missed?
Me, sir.
Only alone, only one, right? You followed this? Any doubt you have?
Yes, yes, sir. I have go through the notes, sir.
That's fine, right?
Yes, sir.
So you see that this for incompressible fluids, we have given total four definitions. All are equivalent. Okay. So and each of them is actually proved. You can easily see. And now this continuity equation for I said for incompressible fluids because we are doing for incompressible fluids. But what we have done is basically when in the transport equation F equal to 1 when you take, that is actually mass conservation law. We actually solved that for any fluid, not just for incompressible fluids. Okay, so we actually solved for everything. So that is what we need to write here. So this equation, that is what we have done here. So how did we do this? When you do that one transport equation and you put F equal to 1, that is actually our law of conservation of mass, because the rate of change of this is your mass when the Wt is varying with time. So that is equal to 0. So that is same as saying, see, that is actually constant, right? So Wt should be same as at time t equal to 0. So if you call it that W naught, so this you convert this into fixed domain, that is exactly W naught it will be. Okay. So at t equal to 0, so this is moving at time t. So once you convert this into function of t inside, so that becomes W naught. So W naught is arbitrary. So what you are getting is this one. Now if you see, for incompressible fluids, you know that J equal to 1, right? So that means at time t is same as rho at time t equal to 0. So rho is conserved. So what is rho? Rho is a mass, right? Density. Density means mass is basically conserved quantity. Rho equal to, for all times it is same. Now this has application if you consider homogeneous fluid. That means rho is only function of t. That means here this will not change. This is not changing. Okay. For all times t also. So for all times t, it is also not. That is also basically mass conservation only, isn't it? So at t equal to 0, for example, right hand side, if you look at it, at t equal to 0, rho doesn't depending on the x bar, for example, on the spatial variable. Here the left hand side also it won't. Okay, so that's what it means. If it doesn't depending on this one, so this is equal to 1 means what? This is equal to rho of 0, basically at t equal to 0, whatever is the rho. If rho is only function of t, for example, that is what is the homogeneous fluid, right? Homogeneous fluid. Homogeneous fluid means rho depends only on the time. Okay. So if initially that is it doesn't depending on the spatial variables. If J equal to 1, the left hand side, this mass conservation basically gives you that. It also doesn't depending on this phi of x of t. Here this is also fixed. It doesn't depending on this variable. Okay, so only this is a function of t. So rho of t is equal to rho of 0. So that's what it actually, that is what is the mass conservation for the incompressible fluids. Okay, but for compressible fluids, what happens? This J need not be 1, right? So that is how it is changing. So this density, if for compressible flow means that means it is not compressible. If J is not equal to 1, that means it is not compressible. So, but this rho compressible, but mass is conserved. So, okay. So this is how the mass the left hand side is this in anyway. In both the cases, mass is conserved. So if you take incompressible fluid, I mean compressible fluid, J need not be 1. But still, initially, suppose it is homogeneous. Okay, that means initially it doesn't depending on the spatial variable rho. That means density. Uh, in general, it need not depend, right? So it need not be homogeneous for all other times also, isn't it? So because of this j depending on the left hand side, so this is not equal to 1, right? So this you divide this side, the rho of 0 divided by j of x of t. So it depends on x, right? So it depends on basically spatial variable at time at different times at time t. Rho of phi of x comma t of t is equal to rho of x. Rho suppose initially it's homogeneous. That means it doesn't depending on spatial variable x bar. So this rho of 0, it will be rho of 0 on the right hand side divided by j of xt. That is actually depending on t and also spatial variable x. So the left hand side at rho at time t is basically depending on both spatial and t in general. Okay. But if you choose, suppose this is if you know what is this one for some particular fluid, and you can choose a row in such a way that uh, you can still make it homogeneous. Okay, so let me give you some such flow. Okay, so let me give you okay, that's what we will do. I think now I will do that one. So I'll take this equation. So what last class what we have done is, this is actually we solved this continuity equation. We solved it. Basically, we see this mass conservation at time t into Jacobian equal to mass at t equal to 0. Okay, that is actually valid for both compressible and incompressible. Incompressible, J has to be 1. So that is, as you see. So homogeneous fluid, if you consider, so for compressible, we will give you some example where a homogeneity can be maintained even for compressible fluid. That's what I wanted to say. That we will do today. Okay, so that particular thing I will take it and I do that one. So the last class you have seen y number of equations, how you have to consider. So 5 equations, 5 things you consider. And finally, when you do this conservation of energy, is actually is equivalent to conservation of momentum in this case. That's what we have done, because the energy is basically comes from the only kinetic energy involved in the system for the incompressible fluids. So what you have seen is basically it's both are equivalent. That's what you have seen. So and then this application of transportation theorem, we give some kinematic condition, because those are now you have the number of equations are 5 and the number of your unknowns are also 5. Now domain is basically you are considering everything as though you don't have the boundary. Now if you have the boundary, for example, for a fluid, free surface fluid, okay, like water, you think on the free surface you should have some boundary condition, right? Similarly, if it is a surface, so suppose fluid is contained in some boundary, some kind of solid inside. Okay, on the boundary you have to give some boundary conditions. Boundary conditions are given by basically your kinematic conditions. Okay, so those that is what you can get it from your transport equation. So we will do that transport equation application and also that example that I was talking about. Okay, so let me open now today's thing. Any questions up to here?
No, sir. Thank you, sir.
Okay. Okay, let's see. So what we do is we consider that rho thing. Okay, so mass conservation. Mass conservation. So you have a different form of mass conservation. That's what you have seen. So rho of this phi of x comma t. This is your spatial variable at time t. This is basically x of t comma t into Jacobian of x. This is only depending on time t. Okay, spatial and time. So this is equal to rho at x comma 0. So this is what is the mass conservation. Okay. So here, if for this is valid for any fluid. Okay. For incompressible fluid, J equal to 1. So clearly you can see. Okay. So for compressible fluid, J certainly won't be 1. And as you see, if initially if the fluid at T equal to 0 is homogeneous, that means rho of rho depending only on time t. Okay, rho equal to, I'll write rho depends only on time. So rho equal to rho of t. Okay, then rho of we call this p of xt t equal to, this is at rho at 0 divided by j of x of t, right? That's what happens, right? Isn't it? From this equation I wrote it. Okay, so implies time t rho of, basically rho equal to rho need not be equal to rho of t, right?
Yes, sir.
If j of xt is not equal to 1, that is for compressible fluids. But you can give, for example, I give you some example where you can think of some particular example. If you give, it shows that need not be the case. For example, I give you, so your space is varying with, so I'm giving you the space like this. Your fluid varies like this. How the spatial domain varies, I'm just going to give you. So example. Okay, so this is an example where we still maintain. Okay, so let me write it. So but we can give an example, but we can give example of a fluid, of a compressible fluid, for which homogeneity is maintained for all times. So let me give that as an example. So what we do is this phi of x t x comma t. Okay, so this you call this, you take it like this. It turns out to be 1 plus t times x. That is your x variable. X variable is changing basically. Y z. Okay, so where x bar is x y z. Okay, so if you take it like this, what is your Jacobian? J x bar of t. What is this one? This will be determinant of, what do you have here? So 1 plus t, this is 0 0, and this will be 0 1 0 0 0 1. Okay, that is simply 1 plus t. So this is at time t, at t equal to 0, j equal to 1, isn't it? And obviously for t greater than 0 and t greater than 0, j is not equal to 1. Okay. So j basically it's that means it is the fluid, that implies the fluid is compressible. Because incompressible only you have that given the definition that z is identically equal to 1. Now how do you maintain the homogeneity? Let the fluid initially having homogeneity. Let the fluid, let the whatever the fluid, that incompressible fluid, occupying this fluid, okay, fluid with the density being what is the density that you give? I suppose I consider the fluid whose density will be like this. So how do I nullify that one? So that is 1 plus t, right? Jacobian. So if I have this, this is over time. If I have something like this, 1 by 1 plus t, if I have, okay, for t greater than 0, okay, then what happens at t equal to 0? Is it homogeneous? It is, right? It depends only at time, right?
Yes, yes, sir. We are assuming this one, yeah, we are getting this one, sir.
Huh?
Oh, so for density equation, we assume this one, yeah, we are getting.
Rho is basically constant in space, right? It's only depending on t. So if you do this one, then what happens? You have mass conservation is followed, right? Otherwise, this need not be. If you don't take it like this, mass conservation need not follow, right?
Yes, sir.
At t equal to 0, what happens? So rho at x, y, z at t equal to 0 is simply 1. Okay. So this is equal to, and rho you have to take it. That is that rho will be 1 by 1 plus t, homogeneity, into the Jacobian is also 1 plus t. That gets cancelled. So this gets cancelled, finally is equal to 1. So that's fine, right? It's maintained. So this is an example of the flow, compressible flow, where homogeneity is maintained. Okay. So you can have a compressible fluid that is homogeneous. Followed? This is an example. That's what we are giving, right? So in general, compressible fluid homogeneity need not be maintained. So here, this is an example where compressibility, homogeneity is maintained throughout for the compressible fluid. Followed?
Yes, sir.
Which you see normally only for incompressible fluids, this behavior. But for compressible fluid, this need not be the case because J need not be 1. But if you consider fluid with this density, then it is. That's what I wanted to give. Okay. What else I was telling? Something else I look at it. Okay, so that kinematic condition, no? So the application of transportation theorem we do now. Okay. Do you understand what I'm saying? Trying to say here? So we have mass conservation. So we are trying to give some example of a compressible fluid for which homogeneity is maintained. For all times, homogeneity is maintained. Where is the homogeneity here? This is true, no? For all times, this is true, right? This will give you homogeneity. And of course, here mass conservation is followed. Okay. So you should
Yes.
have you should go like this. This is with that density with this fluid spatial variable. Okay. So x of t, y of t, z of t should behave like this. With that thing, that's an example that gives you compressible fluid Anyway, so it has a mass conservation as well as at t equal to 0, it's a constant, so it maintains. Okay, it depends only on time, so that is basically homogeneity. Homogeneous. So the compressible homogeneous fluid. So this is also implies we have an example of compressible homogeneous fluid. Okay. So we have seen that 5 equations, 5 unknowns on some domain, wherever fluid is there. If the fluid is having a free surface, we can give free surface kinematic condition. That is called kinematic condition at the surface. So okay. So that is actually is called application of transportation theorem. What is that transportation theorem tells you? Can you just write the transportation theorem? What do we have? Transportation theory, one of the version that we have is this one. So this will give you simply take any version is also okay. So you simply consider the last version. So what is that last version that we have is ddt of integral wt. Okay, at time t the domain is changing. So f dv equal to wt here dou f by dou t plus del dot f u dv. Okay, this is what is your transportation theorem. You consider what is that you consider? Yeah, so this is true for every wt. Wt is a subset of r, which may be varying in time. So if I allow, if wt, okay, so the volume of this, okay, or wt goes to 0. Wt goes to 0 means what? Basically, so you have to say volume of that. Volume of wt goes to 0. What do you expect? It becomes a point, right? So that integral is basically what you are seeing is, let's consider WTB is a typical cube element. It's containing some point x, y, z and t. Okay. So then what is from the calculus, fundamental theorem or whatever, that averaging thing, no? So what do you call that one? Averaging thing, mean value theorem, what it tells you? That whatever the volume, small volume, delta V into F at that one point, right? Hello?
Yes, yes, sir.
Just like Fx a to a to b dx is what? B minus a into f at x star. X star is between and b. See, this is what something similar if you look at it. And you allow AB to be very, very small, this x star will be one of the points. It becomes 1 point. Okay. So then I'm just writing. So what you are getting is ddt of this f, which is same as ddt, right? So f is basically a function of x, y, z, and t. Okay. So I'm writing it here. So that is, you have both inside now. Inside wt is t is varying. So f is basically x, y, z, t. Fixed point equal to, this is nothing but basically it's because 4 variables are there. This is nothing but your df by dt. Okay. So that's what is the left hand side, which is equal to, right hand side is what happens? Dou g by dou t. I mean dou f by dou t. Okay. So plus, what is that you have? Del dot fu. U is vector for you here. That's what happens, right?
Yes, sir.
Yeah. So uh, now you consider your surface, free surface. Let zeta of xt equal to 0 be the free surface. Okay. Think of just ocean. Okay. On the free surface of the water. That free surface you can represent like this. How do you represent? If you consider depth as your z, so zeta of xt is nothing but identically you can think of this as z minus, or this is same as z equal to 0 is identically equal to z equal to some other eta. Okay, z minus eta of, it depends only on xy, that is on the surface, and t, this is equal to 0. Okay, so this is basically the, this is a free surface means any point. What is the point that you have? X, y, z is eta of xy. T is the point is on the free surface at time t. Is on the, any point is on, any point. This point is on the surface, on the above surface at time t. Isn't it? That's how you see, right? Now I want to apply, instead of f, I put it as zeta. Okay. What do you get? Zeta equal to 0, right? So what is that it gives you? The transportation theorem gives you d zeta by dt. Okay. It may be something that is whatever right hand side. Okay. But right hand side is zeta equal to 0, right? So that means it has to be equal to 0 first of all. Okay. By the transportation theorem. Or you say implies this. Okay. With the f equal to zeta. Okay. Is it fine? Why is it so?
Yes, sir.
Because both sides are 0, no? So this should be same as both sides you apply. D zeta by this. So both sides if you apply left hand side. Okay. So that's what is by the left hand side of the by the left side of the transportation, to be precise. So now the right hand sides you write. That should be equal, right? So that is dou zeta by dou t plus plus what do you have here? Del dot zeta u. That's what it is, right? Zeta u equal to.
Yes, sir.
So what is this one? Zeta is nothing but eta, right? Zeta is z minus eta. So you'll have a minus eta t plus del dot. So this is the divergence of zeta means what? Zeta into u bar. So zeta is z minus, right?
Yes,
So how
sir.
do you represent this one? So you can write like z minus eta, right? Z minus eta into u bar. Z u bar. So that you, if you expand it and see, that is also okay. So try to write like dou. So okay, let me write it like this. Del zeta dot u plus zeta into del dot u equal to 0, isn't it? I expanded that one. Okay. So this will give me minus eta t plus what is this del zeta? Del zeta is what is del zeta? Zeta x,
Del
zeta y,
data.
zeta x, zeta y, zeta z, right? So if you do that one minus eta x, so this quantity is minus eta x minus eta y, and then simply 1. That is your gradient of zeta. Dot product with UVW. And then plus here, this is your zeta. Zeta is zeta into,
Zeta. Mm. Z minus.
yeah, z minus. So, but for incompressible fluid only you're doing, right? So there's no meaning for compressible. Compressible thing also you can do. So compressibility means you have to apply this one. Okay. So this is equal to 0. You simply put it equal to 0 since del dot u equal to 0 for incompressible fluids. Okay. It gives meaning only for incompressible fluids, right? Some surface of
Yes,
water,
sir.
for example. So for air, what will happen? So for compressible, if you see, first of all, compressible ideal fluids are rare, right? It's possible, but some kind of artificial thing. So once you cannot confine it to, there is nothing like free surface. It keeps moving, right? It expands. It need not stay, right? Hello? It makes
Yes.
sense only for incompressible fluids. Okay, so this you take it as 0. So what you see is basically eta t. This you give minus if you multiply plus eta x into u. Okay, u into eta x plus v into eta y plus w. That is minus, right? So you are multiplying with minus sign. So the minus w equal to 0. So this is actually the condition. This is the condition of this is the condition on the surface zeta, which is z minus eta of x by t equal to 0. Okay, this is called kinematic condition at the surface z equal to eta of x by t. Followed? So this acts as a boundary condition for you. Okay, so it not only this is the why do we say why don't we say it's a boundary condition? It's one of the boundary conditions because once you have this is like a kinematic condition at the surface, and also your momentum equation is also satisfied there, right? Momentum equation is satisfying everywhere, so that is called dynamic condition. Okay, so if you consider at the surface conservation of momentum equation, okay, if you write it like momentum equation that you have, right, that you have to consider at the surface, right, free surface. Inside the fluid anyway it is satisfying, at the free surface also you have to satisfy. So momentum equation also satisfied at the surface z equal to eta minus eta xyt, and it is called dynamic condition, dynamic boundary condition. Okay, This is kinematic boundary condition and this is the dynamic boundary condition. So you need to look at both the things at the surface. Okay. So because eta itself is unknown, right? So there is something else is coming here. You understood? So this boundary is taking care of that eta. Eta is also unknown, right? Every time that eta you don't know, eta is unknown for the free surface. For that reason, you brought in this kinematic condition, where for the incompressible fluid, where you have this free surface is actually moving. Okay, that's becoming unknown. So this is an application of your transportation equation. Okay, transportation theorem. So this kinematic condition, what it says is basically, if you typically see this one, so this equation condition, kinematic condition, if you look at it, what is W? That that vibration in the z direction. So dou u, that W is what? What is W? Velocity in the z direction, right?
Yes, sir.
So that is equal to this eta. So the eta thing, whatever eta direction, the total derivative. So basically, it is actually not moving. Particle on the surface. Okay, so if you actually see without flow. Okay, so if you consider waves, it's useful when you are dealing with waves. A particle at the surface will remain at the surface. Okay, when do you have the moment at the surface? Either there is a flow or there is a wave. Okay, so wave means energy passing through it. So wave is there means what? The particles are not changing. So only dynamically it's moving up and down. So that is what it represents, kinematic condition. Okay. So if there is a flow, obviously you will have it is varying. So of course that is even if there is a flow, particles are not moving. No. So you're seeing Eulerian description, particles you are not moving. At x, y, z, that you put at x, y, z, it remains there. Isn't it? Hello? No, something is wrong, right? So you have a kinematic condition only for, you think of this fluids where this waves, when the waves are propagating, so that is where you see that the particle at the free surface remain there. Even if you, basically what it tells you that if you move along with the particle, okay, that is also okay. So even if there is a flow, for example, there is a flow, if there is a flow, you have a UV, right? If you move with the flow, the particle remains at one point on the surface will remain there. That is what you are seeing basically. It's basically Lagrangian way of looking at it. You follow the particle, you see that it is actually constant. But when there is a wave, okay, so that vertical direction, that's what it means. See, if you don't think about physically, if there is no wave or anything, just flow is there. UVW is there. For all times it is varying. Okay, that eta is unknown. So what it is basically is telling you that as you move with the fluid flow, the particle remains be there. This is what you are seeing. This kinematic condition is nothing but if you follow the fluid particle, you see that it is stationary. That is what is the thing. Only thing is at the surface, because of the free surface, you have the condition z minus eta equal to 0. You apply this. You apply basically your transportation theorem. So that's what you are seeing. Now, if you consider there is no flow, but you have waves are propagating, due to the waves, maybe there may be velocity, particles may be moving with velocity UVW. So what it says is the particle at that point remains at that particle at the same position. That's what is the W. It only moves up and down. So that vertical direction, vertical. Okay. So if your W is actually equal to, if you move along that X only in the horizontal direction and time, that you move only in that one. So that's what it says. Okay, so that is called kinematic condition. You don't worry about it. You just think of whether there is a wave or flow. Doesn't matter. If you what it says is this is basically total derivative. No, the why all this is simply how you derive this one. This is basically total derivative. Yes, if you move along with the time, it is equal to 0. If you move along with the particle, that zeta. Okay, that free surface, you go along with the time. If you go, basically it remains constant. That's what it says. Okay, that's called kinematic condition. Think of like that only. Okay. So this is one of the applications of this kinematic condition you can derive using transportation theorem. This is one. And now what we do is we'll try to derive. Okay, now what is the boundary condition if there is a solid boundary condition? If you have, suppose you have a you have a water here, you have a fluid inside. Okay, fluid inside here. So if this is a solid thing, if this is solid, okay, this is your D, and this is your dou D. Okay, so dou D is dou W. We said W right earlier. So surface is fluid element is W. Dou W is the surface. At this, suppose it is a solid surface. What is that condition that you will get? If it is a solid, obviously, what is the velocity here? Normal velocity. What is the normal velocity here and here? Inside, you will have some. Okay, so this what is the normal? Normal direction is basically this is your n, right? Normal direction. So u is the vector dot n cap is equal to the velocity with which this dou w is moving. Let us call this u. U is the velocity. Suppose the fluid, the whole w is also moving with time t. Okay. So in that case, suppose it has a velocity u. So right. So some sphere is moving with velocity. So then the u dot normal velocity component is the same as the u is the velocity with which the solid object is moving. So that is also normal. So usually if it is for stationary u equal to 0, where u is the velocity of the object. Object w. Okay. If it is stationary, u equal to 0. That implies u, the normal component of this velocity vector, equal to 0. This is the boundary condition. Okay. So you have now ideal fluid equations for incompressible fluid. You have 5 equations, 5 unknowns. If you have a boundary of a solid, for example, solid thing. Okay, this is only solid thing. And then you have, if it is the solid object is inside or outside, simply imagine some ball is moving inside a fluid. Okay. Then you have this one. So the fluid velocity, that because object is moving, fluid velocity may be changing. So whatever that velocity, normal component, that should be same as the object is also moving in that same normal component. So that should be the condition. So if it is a stationary object, this is your condition. This is moving object. Okay. This you can write it this condition is like moving. All right. Any questions here?
No, sir.
Okay. So what we do is for we will derive, we will try to integrate. We will try to integrate this momentum equation. Okay. So you have some momentum equation, right? So if you try to integrate the momentum equation, which is possible for the incompressible fluids, okay, so under irrotational motion you can do, and also some kind of, so what we'll try to integrate, we'll try to look at the momentum equation, we will try to integrate it. So something like gradient of something equal to something, so we'll try to put it that way. So if suppose gradient of something equal to 0, if you put it, that means whatever something is equal to constant, right? So that is what under what conditions you can get such equation. So that equation is called Bernoulli equation. So we'll derive the Bernoulli equation in this case. Okay. So Bernoulli equation, if you see, uh, why do we do this one? Bernoulli equation. Hello? Why should I do this one? Why should I integrate momentum equation and get this new equation? Already we have equation, right? Why should I do this one? What is that objective? Hello?
Sir, I don't know, sir.
The reason is you are basically considering the same equation. What is that momentum equation only? But under some certain conditions, certain situations, you can actually make it like, gradient of some function. Suppose your equation is some equation equal to 0. That if I put it like gradient of some other thing equal to 0, then that whatever that then it is that means whatever that new something equal to constant you can make, no? So that is same as your momentum equation only. So sometimes that is easier to deal with. Okay, that is actually what you call that dynamic condition that we are talking, no? That is the condition that we use at the surface. Of course, that is throughout the surface, throughout the fluid, that is satisfied because it is a momentum equation that is valid throughout the fluid. Okay, so this is actually equivalent to or integrating integration of uh, momentum equation. Integration of momentum equation. So you ask questions like this, okay? So otherwise you don't know exactly what is happening. So you try to take the momentum equation and try to integrate, you get your Bernoulli equation. So that's what we do. We will see exactly what we do. So momentum equation. What is the momentum equation for inviscid fluid ideal fluid that we have? Momentum equation is, what is that you have? So du by dt equal to plus rho, right? So rho equal to, what do you have? Equal to minus grad p and then plus rho b bar, right? Isn't it? This is what is the momentum equation, right?
Yes, sir.
So this I'm going to rewrite like du by dt plus grad p by rho equal to, let us say, b bar. So external force. The external force, now I consider it as, if I consider what is the external force that I have only gravitational force. If you think like that, then we can replace that F by something else. That B bar. B bar, I can write it like gradient of, you think that this is your Z direction. Z direction is like this. This is the negative Z direction. This is your Z direction. So the gravitation is going, okay, in this direction. So that is basically negative direction it's going, no? So that will have minus GZ. Okay. So minus GZ. Gradient of minus GZ is what? What is that force? So you're acting like 0, 0, minus G. So that is the force. Okay. B bar is this one. That is what it means. So this is your, so you can write like this. B becomes like this. Okay. If the external force is by the gravitation. Now what do you do? I'll try to expand it. I'll try to take dou u by dou t plus u bar dot gradient into u bar plus 1 by rho times grad p. This I'm going to bring it to this side. I'll just leave it there, okay? Minus. Let's write only at the end we will see. So b bar, okay? So that's your b bar. Now you try to calculate this one. So this u dot product with this gradient u bar. So what is this quantity? This quantity, if you actually see a vector thing, this is equal to, I'm writing directly, so we can write like u bar dou u bar by dou x. Can you just verify this one? This is your ith component,
Yes,
okay?
sir. V
And
bar.
huh?
Next one is V bar into dou
I
V
think
bar by dou N.
it should be with dot I, right? So it should be not this one. This is equal to, I'll write it for you. So this is a little tricky. So you just check this. I'm going to put it like u bar dot I cap, okay, into dou u bar by dou x, okay, and then plus u bar dot j cap. Can you just verify this? U bar we has all the components, no? By dou y plus u bar dot k cap into dou u bar by dou z. This is what is your this. Can you verify this one? Just expand. You take u v z, u bar as u v w, okay, gradient as dou x, dou y, dou z, and you see that both sides. And u bar is like no u I cap plus v j cap plus w k cap. Like that you take and you try to see this one. This is a vector equation now. Okay.
Yes, sir.
So it's not just if this is a scalar, then what you are seeing is correct. But this itself is a vector, right? So that is the reason. So you have you need to verify this one. So you just verify this one. Okay. Uh, Once you verify this, and now let's look at what I'll try to give you what I do is I take this first component. First component when you write it, so u bar dot I cap into dou u bar dou x. So this I'm going to write something. So how I'm going to write is this. So I'm going to use this a cross b cross. These are all vectors. Okay. A cross b cross c is what equal to a dot c into b minus a dot b into c. Okay. So this will give me what. So what I have right now there is a dot b c into c equal to a dot c into b. This you bring it to the right hand side, the left hand side of this, minus a cross b cross c. So a is u, b is I, c is dou u by dou x. Okay. So if you write like that, so what I get is u bar dot dou u bar by dou x, that is a dot c into b. B is my a cap. That is scalar. It has become scalar. Now it is a vector. I cap is vector minus whatever you have, write it. So a is, what is a now? U bar cross. What is b? I cap, right? So that is I cap cross dou u by dou x. This is this vector cross product. Okay, so this is equal to I cap. This is the vector. Now what is this u bar dot dou u by dou x? This we can write it like dou x of half u bar square. Can you see this one? Because dou x of u bar dot u bar. So basically you calculate this one. So what is u bar square? What I mean is modulus. Okay, this u bar square means modulus basically. What I have is this modulus. This is what is the meaning. So what is that one? So half into u dot u. Dou x you take it. So what is the dou x? U dot dou u by dou x plus twice you have to do now. So that 2 gets cancelled. So same thing. Dot product is same both sides. So that is what is actually this one. So this, that is what we have written. And this is as it is, minus u bar cross I cap cross dou u bar by dou x. Fine. Now you try to go and put all of them. So for all other components also it will be same. So you go and see, you go and substitute here. So here you substitute. Similarly, you get here. So u dot del u, I'm writing now. Okay, so implies u dot gradient and this del operator on this vector u equal to. Now I'm just putting it together. So if you add this is one component. Another component, same thing will come with j, right? Do you expect the same? U bar dou y, right? Instead of dou x, you get dou y. Okay, half this you norm anyway, you will get the same. Okay, so what is that one? This together is what if I add it? So what you are getting is first one is dou x of half square comma dou y of, I mean this part, these parts if you write it, or shall I write with i's? Put it as I. Go slow, but you go with I. Okay, so this is your I plus dou y of half square j cap plus dou z of square of k cap. Okay, this is one quantity. So when you add it up, so this first term for each of these three terms. Okay, for this first term, for this the first term, for the third term, the first term that you get if you write it like this, minus. Now what is that you get here? Minus u cross. So cross product, right? So this cross I cap cross dou u by dou x, first component, minus u bar cross, you have j component here, dou u bar by dou y or dou, here dou y, right? You expect dou y.
Yes. Yes, sir.
Dou y minus u cross k cap cross dou u bar by dou z. This is what you are getting. So this is equal to. So what is this? This is the vector, right? So that vector you can write it like gradient of u square. So do we normally write u bar that? Okay, you put it like this: square divided by 2. So first three terms is that. Who is this Manvi Chauhan? Okay, so student, right? Who wants to join here? Okay, so this is your first term. So first three terms, if you add it up, this is what is the gradient of something. What happens to the third one?
Can take u vector common, sir.
Yeah,
Minus.
that we can do. U cross. this means what? I cross dou u by dou x. Okay, plus j cross dou u by dou y. What is that one? What is I cross dou u by dou x? So you can do it, right? So this is basically I cross. How do you make the dot product? How do you make that cross product? That is like dou u by dou x only, no? Yeah. Can you just see this one? So whatever you take it out, so what you have is I cap cross dou u by dou x plus j cross dou u by dou y plus k cap cross dou u by dou z. So this is nothing but this I am having minus sign. Okay. So this is basically you just verify that that needs to be verification. Whatever I'm leaving, so you have to do. So this is actually u cross. So this quantity is nothing but you say you just verify. This is nothing but your del cross u. Okay. So del cross u is like ijk dou x dou y dou z. And what do you have here? U, right? UVW. This determinant is exactly what you have here. You just need to verify. So this is actually your del cross u, isn't it? So just verify that. Okay.
Okay, sir.
This you verify so that you can see this one. So this is what I have right now. So u dot del dot u. So if I use this one there, go and substitute. So this implies dou u by dou t plus instead of this now you are replacing with this del this Euclidean norm. So this square divided by 2. Okay. Minus u bar cross del cross u. The reason why we wrote like this is because this is your u bar means what? It's like your velocity component, right? So that is the direction of your streamlines. Streamlines. This is u is the direction. What is del cross u? We already defined that this is your vertex direction, right?
It is
So this is
curl
the
also, sir.
direction of your vertex lines. So u cross w. So if you say omega, if you put it or capital omega, we wrote, I think we define like that. U cross omega. So you can put it like u cross omega. Okay. So plus now what is that you have? Plus 1 by rho grad p equal to b. That is what is exactly your. You can put this now as gradient of g gz, right? So when it comes that side, gz. Grad gz equal to 0. Okay. So this is equal to now let's look at the simplest case right now. Okay. Now we are now imposing conditions now. So what happens for now if I consider uh, irrotational flow? Okay. So for irrotational motion of the fluid, for irrotational motion, what happens? Simplest cases now we are looking at it. What happens if it is the irrotational motion? So what is the meaning of irrotational motion? Del cross u equal to 0. That is del cross u is equal to 0. So if you put this equal to 0, what is that you are getting? Dou u by dou t plus grad of this u bar square divided by 2 plus that is 0. That becomes 0. So grad P by rho equal to plus grad GZ equal to 0. Okay. Now we want to include this P inside. This is grad P, right? This is P and this is rho. Denominator is rho. Okay. So simplest cases I'm considering. So this is, you want to write like this. This implies dou U bar by dou T plus grad of U bar square by 2. This I'm rho, I assume that is constant, is a function of T. Okay. So if rho is function of T, rho equal to rho of T for homogeneous fluid. Okay. So then in this simplest case, in this simplest irrotational motion case, I'm writing. So this is simply gradient of P by rho plus gradient of GZ equal to 0. Okay. So this is what you have. So this is your condition. This is your momentum equation for irrotational motion of, what do you call this one? Rho is rho of T means, what is that fluid? Homogeneous fluid, right? Homogeneous
Yes, sir.
irrotational motion of the fluid. Homogeneous irrotational motion of the homogeneous fluid. Momentum equation basically is this one. Another form. Okay. So what is the advantage? Advantage is because, okay, now you are taking this one. So now immediately here. So here del cross U equal to 0 means what? Curl is 0 means there exists a scalar function phi of x, y, z, t such that grad phi is actually equal to U bar. I want you to, somebody to, so who is that somebody? The last two guys to find this proof. Okay. This is the vector calculus. Open some vector calculus book and find this proof, or and find the Google. Okay. Who is that last? This is an assignment. Okay. So this is one of the assignment for the last. See, I already assigned last class. First three guys, cylindrical and polar coordinate system. You write all the equations, grad, curl, everything in that coordinate system. The next three guys, spherical coordinate system. Next three, next three guys, basically toroidal system that we considered, right? So one of the seventh lecture, you look at it. So all those things, all the whatever the equations so far we have derived, del, gradient, curl, all those things you need to submit. Okay. So once 9 people are finished, the remaining 2, now the first assignment for them is this one. So this is an assignment for
Okay, sir.
Okay.
assignment for last 2. Okay.
Yes, sir.
So these whoever this the 10, 11 BT 10, 11 whatever, whoever, this is first assignment. Next one will come. What is that next one? Next one is basically what it tells you is for incompressible fluid. For example, delta. Right now, am I using incompressible fluid? No. This is not true, right? Did I use any incompressible fluid here
No, sir.
so far? Right? We have not, right? These I have taken only. So far, I have not used any incompressibility here, right? So if any fluid, compressible or incompressible, if it is irrotation fluid, you will have, once you have irrotation fluid, del cross U. The curl is 0 means there exists a scalar function such that del gradient of phi equal to U. So this is your first assignment. Find out on Google, understand your own way, write it neatly, share it to others. At the end, you are going to share it to everybody so that they will go through it, so they know that they have proof for this. Okay. So this is your first assignment. Next assignment will be del dot U equal to 0. Suppose you consider incompressible fluid. Del dot U equal to 0. Immediately I can find similar way there exists a vector valued function which is of course not unique. Here it's unique. Okay, there exists a unique. This is important. So here the unique phi such that the grad phi equal to u. Now there del dot u equal to 0 means there exists non-unique vector field such that, okay, there exists some vector field such that uh, that u del dot u, right? So u equal to it's a curl of that vector field. Okay, so that is your next assignment. So I'll write it first. Let's use this one here. So this implies what will happen if I use that one. Dou u means that's finally gradient of dou phi by dou t, isn't it? I can take dou t out, right? So u bar I'm writing as grad phi. So this is what you have. Plus now grad I take it out, so you will have a u bar square divided by 2. Now here p by rho, everything function of x, y, z and t. Okay, so this one plus gz equal to 0. Okay, so this means dou phi by dou t plus half u bar square plus p by rho plus gz equal to constant in the entire fluid. Entire, what fluid is this? Irrotational homogeneous fluid. And this is called Bernoulli's equation for irrotational. Okay, just this is called Bernoulli's equation. So don't repeat everything. Okay, so the next assignment I'm going to write here. So assignment for this, so next assignment will be now if del dot u equal to 0, then there exists a vector field What is that vector field? Let's call this. Give me some notation. What is that vector field you want? Let's call this. Oh, what do you want? Vector field V. V. Shall I put V?
Yes, sir.
Yeah. Vector field V. V. We are not going to use anything. So let's put the V such that we are writing careful. So it's only A. Okay. So such that U equal to, like earlier, U is grad phi, right? So here del cross V. Why is this not unique? So I'll try to add divergence of any, if I add this to, what is the divergence of del dot gradient of any scalar field? What is this one? This is not be 0, right? Yeah, del cross. You're going to add, no? So to this you are going to add. Yeah, it's okay. So del dot del dot del cross del phi, okay, is always 0. If you use this one, so I can add instead of V, right? So I am going to add some grad phi. What will happen? If you add del cross this one, del cross this, and del cross del phi. Dot product, this is because this is always 0. So if I add for V, if I add any grad phi, that is still it is satisfying, no? So that's how it is not unique. Okay, do you understand?
Okay, sir. Sir, this assignment for everyone, last one.
No, last two guys. This is another small assignment. Okay, so this is another one. So this del dot u equal to 0 means there exists a vector field such that this is basically Helmholtz theorem. So Helmholtz, just look for Helmholtz theorem. That is what we will give you. So look for Helmholtz theorem. So what it says is Helmholtz theorem basically tells you that u is given as a rotational component as well as irrotational component. So basically irrotational component means v is given as some. So basically you are going to write like del cross del phi, del cross del phi. So you put it like this. So if you do this, divergence of del cross this is 0 always, right? If you put this, this is your irrotational part. Okay, so this quantity is the rotational part. Someone wants to join this call. Who is, what happened? Kush. Okay, so you see, basically Helmholtz theorem tells you that any vector field you can write it as two components. One is the rotational component, other one is irrotational component. Okay, so that if you do it, so you will see that one you can actually find that one. So this vector field. Okay, this is an assignment for you for the last 2 days. So one is this. One is this one, grad phi equal to u. That is an assignment, and this is also another assignment for last 2 days. Okay.
Okay, sir. Sir, when we
Yeah.
have to submit all the assignments, sir? On which
This,
date?
you try to see. You know you don't know this one, right? So if I start doing it, it takes another 2 to 3 hours. Instead of wasting time asking you to do, this is simple vector calculus thing. So you look for and try to find out, and as soon as you make it and submit, then you basically submit email not to me. You will only get few marks, 5 or 10 marks. Okay, those 2 guys. Those, but if by doing this and submit to everybody, share it to everybody, they will learn, right? Everybody will learn now. You know the proof.
Yes,
You
sir.
understand? Similarly, all those coordinate systems. So whatever those equations in other coordinate system, that is just a routine work for first 3. Okay, first 3, second 3, third 3. So for all 3, I have given already that work. These 2 things for the last 2 days. This is simple work. You just look for exactly, try to understand how you get that gradient of phi equal to u for irrotational flow, and incompressible flow, how you get this vector field v. Okay, that is basically, I'm giving you a hint that is basically you look for Helmholtz theorem. Helmholtz theorem, if you do, that is exactly what you want, right? So you ignore this part, exactly what you are asking. Del dot u implies there exists a vector field, a vector. This is a rotational part is basically your vector field. That is what I'm asking. Irrotational part, you leave it. Okay, but that will come as a bonus with the Helmholtz thing. Okay, followed?
Okay, okay, sir.
Yeah, okay. So we will continue next class. That is tomorrow at 11. Okay,
Okay, sir.
same thing will continue. Yeah,
Okay.
I'll see you
Okay, sir.
then.
Thank you, sir.
Thank you,
Thank
sir.
you. Yeah.